Mm, I am going to talk about four elements. And I'm quite interested in sun and the earth. Old ancient Greek people or the Eastern people thought the world consists of fire, soil, air, earth. And nowadays, we think about it, fire is the sun, air is the atmosphere, and earth is land, and water is fresh water and salt water on the earth. So I can talk about here. Here is the sun, big sun. Sun itself fire. Sun give energy, all the direction. Not even sun itself rotate itself, and also sun has what is it? Solar system, and we can guess because this is all fire, and all area of sphere emit like a radar and sound. It goes out energy inside to outside. Simply, and we can call it light. So, and its ratio is same with the area of the spheres. So, and this area is radius is Rs. This is radius S plus T. So, and the energy mountain, solar energy here, 4, 5 R square as amount of energy also equal, and solar energy 5 R radius S to D square 5 4 5 radius S to D is equal. And this is very important. Why it happens? Because and then if they're same areas, this is a large area. If there is 10 light and then 10 particles of light, and this area is also same 10 particle, because and same ratio, and then the area is very wide, and this is more powerful. This is less powerful. Okay, so this is sun, fire, and go the light to where to? Go the light to. I'm going to draw this. The direction is not matter because there's a gold light Earth. This is Earth, and direction is no matter because Earth like revolve the sun with the orbit here, and also it doesn't matter. Maybe we can imagine if the Earth circle like that, and the same situation. But normally, and all the planets revolve the sun in terms of sun's rotate itself because of gravity. I'm not sure that. Anyway, so here you go. The light go and also go here. All the direction with the spherical direction, not the only line, not the only surface plate. And then this solar energy I calculate about A times 10 minus 8. All of the solar energy at the moment in here is the spherical area. So, and very tiny solar energies comes to the Earth. And also, and we can see here, the solar energy is only bright the half of the Earth every time. Just the Earth and then rotated and revolves with the 23.5 ethics, and so and something changed every day, especially revolution. So, and I'll talk about that. The one important thing is about solar energy on the Earth. How can we figure out solar energy on the Earth? Here, Earth, and maybe the layer is atmosphere. Atmosphere very important on the Earth. The thick line is atmosphere. And I can get vertically and here the line to length of including atmosphere. And there is a sunlight. There is a light. And then the light comes, and this is actually the circle. This one is the Earth's sphere. And at the moment of the sunlight passed through the circle and reached the Earth. As you know, the speed of light is 300,000 kilometers per sec. Very fast. We cannot see how the light is fast. Maybe some scientists measure the amazing speed scientifically. They are awesome scientists. Interesting. You try how to measure the 300,000 kilometers. Amazing. So what I'm talking about, and most atmosphere and maybe 100 kilometer or more than there's atmosphere is from an exosphere. This is about more than 1.6 thousand kilometer. Anyway, whatever, and there I can say 100 kilometer or more than, and that means this part is 100. This part is 6,478 kilometer. More than 7 is okay. So what does it mean? That we can calculate this and 300,000 and 300,000. I can get, and then the speed of moment, the second, A3000 to maybe 150 seconds at the moment of speed. So I can say that the same time same time. Okay, the end one. I'll talk about solar energy. This solar energy is not the solar panels, but sunlight itself. And this is the second lesson about the Earth. And nowadays, I watch this the Yale course lectured by Professor Lon Smith, and his lecture is very good about Earth's atmosphere, environment, and um, uh, all about the Earth. It's quite interesting. Okay, let's get to the point. I talk about and solar energy from the sun, and then now I'll talk about and the equality, how measured here. Maybe I can draw. This is invisible light. Invisible light. And then this is Earth, and this is atmosphere. Maybe 1,000 kilometer, a little bit long, thicker atmosphere. And here on the circle. This is actually like this circle. The Earth is like this, maybe measured like this globe sphere. In here, there are two cases. When we talk about the Earth, the globe, not the atmosphere, and then we can calculate the circle is a little bit different, small one. We can talk about atmosphere a little bit bigger. So, and then this are equal, and then R Earth, and bigger one, and including this R1 and this R2, this is our atmosphere, height, altitude. So, as I mentioned, the solar energy at the same time, and this is solar energy is at the same time. This is unique, and then basically beginning of ideas. As you know that the area is 5 r square, and then grove half of area is 2 5 r square. Interesting. We can view that at the moment of this solar energy equal amount this solar energy from this solar energy, and then this is a sphere, this is a circle. So, and then we can view very differently. And for example, the Earth almost and here Earth's view is from the spring equinox or fall equinox, and also tilted 23.5 axis when the sunlight go, and then when the sunlight here, and then the all latitude here, all latitude have the same daytime and night times, and so and the sunlight and equal just a few days, not long, but while revolving the sun revolving the sun, the earth revolving the sun, and then this angle, axis angle is changed, but interestingly, this is the same. This is go for summer solstice. This is go for winter solstice. Summer solstice and winter solstice. And we can guess, and this part, and this part, and this part is angle is almost the opposite. So, and then the amount of energy, maybe we can guess the same. And also one thing is the sun always lights the half of the earth. So, and then we can guess and how much solar energy goes to the each latitude area. And the Earth, when we study about the Earth is like this, and this is equator. This is 23.5 latitude here, 23.5 latitude here. Two line is very important in Earth environment. And the Tropic of Cancer to Tropic of Capricorn, and also the polar zone, and this is 66.5. This is polar zones, and we call this is a low latitude, and then middle latitude, and upper latitude, high latitude. We can meet each different climate regions here, and this 40 is tropical rainforest, most of them. This is temperature zone, this is polar zones. And in terms of solar energy, this area is almost the same here. Large area, and also this area is same like this, large area, but the polar zone is very small area. So why it happens? Because there's angle. Globe is got angles like curved, like circle curved, and this is basically the angle line is the length is cosine theta. The cosine graph, we can get cosine graph here. First 1 means r to down to 0, like this. So, and this angle part, when we go for 66.5, almost here, 66.5 here, 66.5 means the latitude north 66.5. The angle, the sunlight directly comes here, and then reach here. This area, actually this area is very wide. Area is wide, but and then the amount of solar energy very rare. And this is really pointed. So when I measure the amount of energy, 1.69% of all solar energies, and then maybe. So quite interesting. Maybe perform 50% because of half. And then yeah, it's quite interesting fact. I'll talk about circle and the sphere. That means circle and the Earth. It's quite circle and Earth is related to each other. Here's the Earth. And then atmosphere, the Earth's atmosphere, same lines, almost. Basic atmosphere is 100 kilometers, exosphere 1,000 kilometers. I can get, this is angle, this is a circle. There is a sunlight. Sunlight comes. This is a circle. So when we can imagine two circles, this is circle, this is a sphere. This is circle, this is a sphere. And then directly the sunlight comes here. And at the moment of sunlight, energy is called solar constant. See? Measured here the Earth's solar constant joule per meter square each second. One thing, and the area is here's the 5r square. This sphere area 4πr square. That means at the moment of energy is maybe 4 times here. Solar constant in circle 4 times 1732 joule square. I'm not sure, and almost this number is similar, not clear. I need to check. So what I'm talking here is very simple about area difference and also relation with this circle and the sphere. Interestingly, the relation is angle is same relations. We are here the Earth. We use the Earth and without angle. This is angle. We can guess this is moment, and this is equator, and this is North Pole. At the moment of spring equinox, it's possible for equinox. It's just one day. And here, interestingly, we got angle. This angle, So, and the sunlight directly comes here. And this angle means theta means latitude. It's very important to observe the Earth, especially Earth surface. Our surface is 4πr square, but our surface means and oceans, continent, where we live. So, and then we can measure the latitude, and even each time just the big circle, many circles went by rotation, the Earth's rotation like this. At the moment, the circle, vertical circle get the longitude. So, and then we can exactly measure the oceans, continents relation with this circle with the solar constant. So how the angles impact here, and then I can see this. Maybe line is here. This is the center of the circle, center of the Earth's globe, line of the here, and this line is theta. That means latitude theta, and here one. This is same theta, and that means we can measure when the solar constant energy here, and then when the 24 hours is all day because of one circle around here, and this is 24 hours same. This area is exactly this is H. So and easily we can calculate it. This one is 2 pi r. H equal sine theta r. This is the area of the Earth, and that means this is 2 pi r square sine theta. The amount of solar energy one day and the amount of solar energy the one day is same. The area is also that can measure the equals. That means one moment it is the same, so we can get how related with this area to and then solar energy used. And also when we see the phi r square 100%, and then we can measure how much this area, that means this areas huge, so 8% from solar constant energy. So, and this is very important because by doing that we can measure each part, ocean, continent, or countries, and many specific regions. Calculate how much is solar energy can each ocean or continent countries use here. By doing that, we can understand the Earth, especially like the polar zone, how much solar energy used, and then so by doing that we can figure out how the Arctic ice sheet and it's going on, and then like some pact or then global warmings made by man and some CO2 or loss of we can talk about it. It's quite interesting, and this area is simple because 2 pi r square over 2, and then minus these areas, and then we can these areas measured, and like this is theta, 2 theta, 180 minus 2 theta over 360 pi r squared. This is area. This is pan area, and then also this area is same two triangle. This triangle is sine theta r cosine theta r times. So minus we get. This is lesson 4. I'll talk about the sun and the earth and the sunlight and comes to the Earth at a speed of 300,000 kilometers per second. And we can guess at the moment the sunlight comes to the atmosphere and almost 100 kilometer per kilometer area, and then we can think about this the moment, because one 150th second maximum second, and then comes to the Earth. This is at the same moment, and our solar constant energy comes from the solar for 365 days. So that is what I am talking. The basic theory is solar constant energy. The circle and the Earth quite related each other. Mathematically, we can get area with the same angles, means latitude. And and then I measured how to get latitude using Pythagoras theorem and trigonometry. It's quite interesting. And then now today I'll talk about how much the polar zones use the solar energies a year. Then with percent, and 100% solar constant energy, the Earth. And basically I got the answer 2.831%. It's not much. And then in terms of the wide areas, polar zones is actually wide areas. Maybe polar zone is lots of oceans. I'm checking out, and then the area, the Earth next times. How to get and the percent that the polar zone user. And okay, very simple. Polar zones, we have 66.5 degrees in terms of 23.5 axis, and then we have 47 degrees with the circle, and then actually we got two departed the areas, the very small areas, and then I can measure these formulas, and there's two times, and the angle is 47, and this, I can get these areas, the 47 per 360 degrees 5 r squares minus this right angles, and then sine 6.5 r times cosine 65 r, and after that I can divide it by pi r square, and then I can measure this number, and using pi and r squares divided, and then 47 over 180 minus 2 sine cosines over 5, and I calculated with my mobile phones and the calculators with the sine cosine over 5, and I measure this, and 0.02831. That means this area use 2.831% of solar constant energy. When the summertime, this area is tilted like this from the sun. That means this area is almost 50 north 50. And hardly in summer times, hardly the energy is very high, solar energy very high. By the way, the winter solstice, this go no sunlight this area. Even though the position is quite different, and then at the time cold, very cold. So and we can guess year by year, and this area energy is almost the same. We can guess that. So we fixed this energy on 2.831% because this is increasing solar energies. This is decreasing solar energy. The ratio is the same. So and mathematically, not the solar energy functioning is quite different. Figure out next. Mathematically, this amount is same. And when we got evolution, we can get at the position of this. So and we can 2.831%. So with this percent, considering global warming or climate change, some seasons highly affected by the solar constant energy. So it could be happen, and all the ice sheets melting down during this. But then go here again, and snow and fall and again frozen. This is repeated 1, 2 every year, repeated. How long? Undoubtedly 1,000 or 10,000, million, billion. In terms of history of Earth, we can go and back maybe million years. So and this is our story, not humans. And human effect here, summer seasons melting and affect the global warming. So what I'm talking here, global warming or climate change affect the Earth. This is man-made, but the Earth system is beyond humans. Human could not affect all the solar system or the Earth itself. As we say, and we borrow our environment from the Earth for our offsprings or other creatures. So we should think about and point different view with the climate change. And then we needed to study more, not the Earth's effect, but not only Earth's effect, but also human activities and harmonizing, thinking about more poor countries, thinking about more developing countries, and there are many things to think about reasonably. Lesson 5, I talk about the sun, usually solar energy, constant energy, and then the amount of solar energy on the Earth. First of all, polar zones. Mathematically, in the amount of solar energy in particular region, country, or local province or ocean or lake, it can be measured in percent. Knowing the percent, and we can understand and the area, how is the area affected by the solar energy, and we can understand more the environment of the earth. Now I'll talk about and Aristotle's four main components which consist of the world. Aristotle talk about fire, air, soil, and water consist of the world. So here I am talking about here in Aristotle component, which consists of the world. This is fire, air, soil, and water. Here, fire is the solar energy, sun itself, and air is atmosphere, and soil, crust, and water, fresh water, salt water. Aristotle lived a long time ago, and then Aristotle lived and then before Christ, BC, maybe 260 or 200, maybe 300. And Aristotle was a student of Plato's and teacher of the great Alexander. And at the time, we cannot and he didn't think about solar energy and didn't think about atmosphere, which makes weather or climate, and didn't think about crust and water. So it expanded the idea from Aristotle. So I mentioned about the solar energy, which directly reach the Earth, and now I'll talk about atmosphere, crust, and water. And when solar energy comes, and there's atmosphere, and the solar energy, the sunlight itself penetrate. Most of them penetrate the atmosphere and reach the here land or Pacific Ocean, land and ocean. And according to the scientist, and 100% the sunlight penetrate 67%, 33% remain atmospheres. There are many gas layers from the atmosphere. The sunlight hit the gas areas through when they penetrate the atmospheres, 37%, 67%. So, and then here again, this is Earth. This area is atmosphere. We'll learn about atmosphere layers. And here, this is land. Maybe this is outer sphere, outer space, outer space. We can imagine that outer space is a little bit black. We don't know still, and people don't study this outer space much. And people talking about other stars by observing with the telescopes, but black question, still question. Anyway, so and then outer space almost 1,000 miles. That means 1,600 kilometer. There is exosphere, and I don't mention about sphere. Sphere means globe. The atmosphere. Atmo, maybe Greek word. Atmosphere. Atmo means I think air. I'm not sure that in Greek. What I guess. So it's isono. Exo is quite long range. Isono, they are both of them temposphere. Temposphere. And also next mesosphere. Next stratosphere, and so thermosphere. Thermal. I'm not clear that spelling. I need to. And so, and there are main four layers: thermo, strato, meso, tempo. Tempo consists of isono, exo. And then, actually, I learned. I didn't study because I have no any studying from the science, and especially Professor Hu and Lon Smith. Here, this is temperature 288 Kelvin, and this is Earth's temperature. It means evolution. Earth's temperature go down, and same area high, and go down high, like that. But this area is a 10 kilometer range. This is 8 kilometer. This is not much, and maybe I'm not sure that. So not long range is the thermosphere, and this area is quite large. Exosphere is very long. The temperatures down, up, down, up. This is atmosphere. So, and then a little bit I'm going to study more about atmospheres. Okay, today I'll talk about water. Talk about the sun and the earth and atmospheres. Maybe I need to talk about atmosphere again, but here, and I'll talk about lesson 6. The topic is water. I can make a water clock, water temperature clock. This is the Earth. In terms of water, and the Earth's surface is 70% consists of water, 30% consists of land. So water, and so most of area is water, especially salt water. We can guess here North Pole. This is South Pole. And we think about this is prime meridian. This is meridian. Now, and isn't it like a clock? Almost same. And then we have latitude through the Earth. This is the equator. Let's see and about the water temperature. And here, this is Arctic Sea. And North Pole and Arctic is actually the sea. And maybe up here, so this is 180 east or 180 west. And this area, maybe this area is Bering Sea. This area is northern Pacific. All the Pacific, and an area is a very important part trophic cancer. Equator. And this part is water temperatures effect, and then importantly El Nino. El Nino. El Nino. No, not clear. And then here is a trophic Capricorn. This whole area is interestingly all the Pacific. And then Antarctic Sea. Same here. Antarctic Sea, Atlantic Sea, Atlantics. The Atlantic Sea. Same. Almost this is Mediterranean Sea and Atlantic, and same Arctic Sea. This is when we think about this is water temperature, and water temperatures up and down in spring, fall equinox. What I mean, after spring equinox at the northern hemisphere, the water temperature like here, and slowly up. Water temperature. This water temperature, for example, and 5 degrees Celsius, slowly up, and then 5 to 5 March and slowly up, and 22 September. Fall equinox and slowly down. Go for again spring equinox 5 degrees Celsius, and again 3. Here 6 months terms. This is water temperature also is affected by Earth revolution, and all areas are all the same. And this area and tropical rainforest area, temperature area, little bit different patterns. So when using this water temperature clock, maybe we can figure out how the water temperature go on. Maybe we can make looks like digital functioning, and the line is latitudinal line, so we can change latitude by doing that. That is what temperature is also, for example, go for another part, and we can go for the Black Sea or Caspian Sea. And so yeah, we can learn about the water temperatures. Okay, water temperature is very important. Most of evaporation on the earth happens in the water, and the change of climate comes from water. So when water is very important, and basically water evaporation, and again precipitation. Sometimes in rainy season, most of area lots of flood. This flood affection by climate change gets increased and also more powerful. So and then we needed to learn about water and temperature. By checking temperatures, we can predict how much rain comes in rainy seasons, and also we are prepared that kind of happenings. All areas are almost the same. Okay, now water.